In today's session, we'll have a discussion about friction. So the argument goes somewhat like this. Um, let's say there is a crate, an object, and in this case, it's not a mysterious object. So there is some friction between the two surfaces. Wait, I'll try to show it as if the two surfaces are in contact. That will be better. Okay, and let's say that you start pushing against this with some amount of force. Okay, some amount of force, F1, let's say. Now, naturally, since there is some friction, the crate is not going to move. So what is this friction that does not allow the crate to move? Basically, if you look at the surface of the crate, sorry, I have a new graphics tablet and I haven't quite mastered how to use this well. So bear with me for a few classes. I'll get it right in a while. So what is happening between the two surfaces, the surface of the crate and the surface of the floor, is that microscopically when you look at it, these two surfaces, however smooth they may look to the eye, are actually not smooth. They have these sort of valleys and cliffs that kind of interlock between one another. Okay, and it is this interlocking of these valleys and cliffs that provide the friction. Because when you're trying to move one object, see this object, the great part of it is trying to move in that direction. So naturally, these interlockings are going to provide a resistance which is going to oppose it in this direction. And basically, you can understand friction from that point of view, that all the tiny little forces that are preventing the upper object from moving add together and create the force of resistance. So that force of resistance is what would amount to this frictional force. Hey, I changed the color. Didn't change. Yeah, now we got it. So we can put that as the force of friction. So now coming back to the same situation, when the force of friction, when you are pushing against the crate, the force of friction will naturally grow. So let's say that you apply a little bit more force, and now you are applying a force F2. So I get rid of this F1 and the force that you are applying now is a new force F2. The force of friction also responds to this. Okay, so the force of friction will also grow. Why? Because you are pushing harder against the valleys and cliffs, and the valleys and cliffs are providing more resistance. So as your applied force increases, as this force increases, this force also increases. So the crate is not moving at this point of time. So you have a situation where you have a static equilibrium. Okay, so sigma f is going to be equal to 0 because all the forces are equal and opposite. Now, how long does this situation remain? Well, the situation obviously remains until the force that you are applying is sufficient to break free. So what will happen is these jagged edges are going to jump over the cliffs and valleys at the bottom side, and then you have broken free. So the limit, so there is a maximum limit to this force, the force of friction. Okay, and once that maximum limit has been reached, obviously the object is going to break free and start moving. So this maximum limit is what is known as the limit of static friction. Okay, and once the static friction limit is overcome, then the object is going to be set in motion. So now we understand what is static friction. You could ask, well, what does the static friction depend upon? And there are some surprising finds. The static friction limit actually depends only upon the materials that are in contact. Okay, which means that the materials that are being used, say for example, the crate is made of wood and the floor is made of concrete. So there is a static friction limit for concrete on wood. Or if the object is crate is made of rubber, there's a rubber lining at the bottom, and the surface is made of, let's say, tar, like in a road. Then that has its own static friction limit. If the floor happens to be marble and the crate happens to be made out of, say, steel, then that will have a different static limit. So that is what I mean by saying that the limit of static friction really depends only upon the two materials that are in contact. Surprisingly, the surface area of the two materials in contact does not matter. Why it is so, we will see it later if necessary. I will give you a link to a video of a lecture by Professor Walter Lewin in which he attempts to explain it by showing some demonstrations. You can have a look at that. So the basically the surface area does not matter, and of course, gravity does not play any role in this because the surface is flat. Now, we come to the next situation. So once the static friction has broken free and you start pushing, in the assignment, I had asked a question: what about the amount of force that is required to keep the box moving? So once, sorry, I'm not able to draw the horizontal lines well anymore. Okay, so yeah, once the crate has broken free and it's moving, then what is the amount of force that you have to apply in order to keep it moving? Now there is something, again, if you look at it in terms of the valleys and the cliffs kind of an idea. Now what is happening is the valleys and cliffs are not being able to interlock with one another. So that's what happens when an object is moving, right? It does not manage to lock into one another. So when they don't lock into one another, the amount of force that is required to keep them moving is going to be lesser than the static friction limit, right? So the amount of force that you are going to be required to apply, let's say this is force 3, right? Wait, let me write that properly. Okay, the force that is required to keep it moving is going to be lesser than the amount of static friction. So this is a dynamic situation where the object is already moving. So here we can see that the maximum static friction, so this force F3 that you are applying, is going to be less than the maximum static friction. I'm going to put as S max. Okay, I hope you understand that the force that is required in this situation to keep it moving is going to be less than the maximum static friction. So therefore, is there any friction at all between these two surfaces? Yeah, of course, there is friction between these two surfaces. There is a friction that will resist these two situations, but that friction we call as dynamic friction. Okay, so it's the dynamic friction or the sliding friction. Your textbook calls it the sliding friction. This friction is going to be also naturally less than your static friction maximum. Okay, so this I'll just label over here is dynamic friction. So to answer the second question, if you want a crate to be moving at a uniform velocity, then how much force will you be applying? What is the amount of force that you will be applying? Well, the answer has to be equal to the amount of dynamic friction that is there. Because if this F3 is equal to the dynamic friction, if F3 is equal to FD, sorry, that looks like a 3, but I mean, that looks like an S, but it's 3. Then you have again sigma f is equal to 0, but in this case it's a dynamic equilibrium. Okay. Um, and then we come to the last situation in which the question is asked, well, if the object, once it starts sliding, then does the velocity of the moving object matter? So I'd like you to think of a situation of a car um, going on a road, and let's say it starts raining, and suddenly the friction value between the tire and the road reduces because of the presence of water. So the car can start skidding, and believe me, this is a real situation. It does happen. Um, Now, the maximum amount of friction that is available between the tire and the road. So sort of just roughly draw that situation. So tire and the road, right? The friction that is possible, maximum possible friction between the tire and the road, um, has a value. And once the tire starts skidding, right, the maximum dynamic friction that will be obtained will be reached, right? So the velocity with which the object is sliding does not really matter anymore. The dynamic friction value may increase a little bit or decrease a little bit with the change in the velocity, but it's not going to do much. So therefore, if you are skidding on a high velocity in a car, it's going to be more dangerous because the friction that you're going to get between the road and the tire is going to be exactly the same. So it will take much longer for the vehicle to come to a halt, even though there is friction. Therefore, creating a more dangerous situation. And in the answers to your questions, I had mentioned more dangerous when it's in a car, and it can be more fun too. Where can it be more fun? Well, it can be more fun when you are, skating. Say, for example, we don't skate much in India, so the only situation that I can remember is if you have a nice smooth floor, and you wear socks and you come running and you slide on the floor. I'm sure some of you have tried this before. The faster you go and the faster you start sliding on the floor, the more fun you have because the longer then you can uh, slide on the floor. So in that way, it could be fun or it could be dangerous depending upon the situation that you are in. So I hope the idea of what is static friction, what is dynamic friction, what is the difference between the two, um, what are the peculiarities of friction itself, that is what what friction itself is caused by, that is understood. And also that um, friction is a strange kind of force. Sorry about the rooster crowing in the background. Friction is a strange force in that it depends only upon, mainly upon the two materials that are in contact. So I'll stop here now. If you have any doubts or questions, please write into me.